Hi everyone! It seems like only moments have passed since the last video. This thing has been incredibly time consuming, and you'll see what I mean as I'm going through this video here. Just below this video are a bunch of attachments. Those attachments will allow you to build this project the exact same way that I've built it, right down to the project box. And when we get to the project box, I'll explain that then. What you see here is actually one of the attachments. This is the layout for the back side of this board. Now, this is modified a little bit since the last video just to make it more sensitive to test mica capacitors and to do a bunch of other functions as well. And once I get this entire project done, we'll do some experimentation with this and I'll show you how incredibly useful this thing is, and that goes well beyond testing capacitors. So this is a really neat device. Now, I'll show you the modifications on the schematic here. It really isn't a whole lot of modifications, but there are a bunch of things that you can do to make your device more sensitive as well. So what I'm going to do now is I'll move this out of the way and I'll get the schematic. We'll take a look at this design here and I'll show you exactly what I've done on the circuit board and why I've put the pieces where I've put them. Here's the modified capacitor leakage tester schematic. And the reason it's modified is because we want to test micas and electrolytics. Another reason that it is modified is because we've taken the circuit from a breadboard and we've put it onto a circuit board, and things get optimized when we do that. We lose a lot of capacitance and inductance and things like that. And finicky little ICs like the LM3915 and the LM3914 like to act up. So I have to add a whole bunch of little components in here to keep the thing settled down. Now, some of the components are added not just because, the thing is acting up. It's more of preventative maintenance. I know that this IC is, basically they're done. They're not being produced anymore, and the same thing with the LM3914 as well. So that means that down the road, chances are you might be getting some of these things offshore, and they might act just a little bit different, and they might be a little bit more finicky than these things. So in order to make this, pretty much a solid design, I've added in a couple of components for some built-in redundancy, I guess you could say. So basically to keep the circuit calm, and I'll go over that here in just a moment. So what we'll do is we'll talk about the mica and electrolytic settings here first. So I've added a switch. This is a 3-position switch. So basically you can click this one way, like so. It's center off, and then this position here. So basically we have 3 settings with a center off switch, which is kind of nice here. So I've managed to get away with just using this. So basically what's happening here for testing electrolytics, you can see that we have an 82K resistor, which is brought to ground here. So that'll allow us to charge capacitors faster, and it'll test the capacitors at about 7 microamps. So at about 7 microamps is where this LED extinguishes and it goes to green. Here's the thing, you want to make it more sensitive than that. You want to test them at 2 microamps, 1 microamp, or even into a completely different range. Just up the value of this resistor. So take this to 100K, 150, 200K, and you're testing capacitors way, way, way down in the microamps, and even beyond. So it's all up to you. I have an 82K resistor here because it's a reasonable amount, and I'm not going to be waiting for days for the capacitor to charge, right? Now, this thing here is set up when you're testing capacitors, right? We're using 27 volts. So basically, all the capacitors electrolytics that you test will have to be beyond 27 volts. Here's the thing. You want to bring this down to 5 volts. You want to test 5-volt capacitors. Very, very easy. See where this 4.7K resistor is on this end here? Just put a Zener diode to ground as a shunt regulator, and it'll hold it at 5 volts or 10 volts or whatever. And you can put a little rotary switch in there if you'd like. And by putting the rotary switch in, you can select different voltages right up to 27 volts. Very simple to modify if you want to test different voltages. So again, leakage current here and voltage setting up here. And this will be some trivia here. Why is this diode here, this 1N4007? You can answer that in the comments here. This will trick you. So why is this here? I'll be looking forward to reading your answers of why this is on this line here. Now, let's see, what else can I tell you here? There's a capacitor across the red LED. Now, in here, there is no more green LED. There's a green LED that indicates okay, and there is a red LED that indicates that the capacitor is basically, well, you know, when the red LED is on, you can be considered bad, or, you know, basically it's charging until the green LED switches. So before I had two green LEDs, now I'm using a high brightness red. And it'll work out very, very well, and you'll see in the completed project, it really accents the project as well. Now, there's a 100 microfarad capacitor across this LED, and the reason that that's across this is because in this setup here, when these LEDs start to count down slowly, so this is moving down and it comes to here, and then it's just about to switch to the green LED, if it moves down incredibly slow, the hysteresis between these two LEDs here will cause these to bounce back and forth, kind of like a ball almost, on a very slow charging capacitor. Now, I don't want that. I want this to just come here and then nice and clean switch to the green LED, and that's the reason that there's a capacitor across this red LED. Now, this can be put in a bunch of different places, and you can also use a much larger value capacitor in different parts of the schematic to cause this to, you know, basically to switch nice and fast here. This area right here across this red LED was the best area to add this, and this here seems to be about the right value. Now, that was found out through experimentation. And whenever I design a circuit board like this, I go into this fully expecting to build more than one circuit board. And as you can see, that has been done. This is my experimentation board. And this is where basically I work out all the issues that are created in the transfer from the breadboard to the circuit board. And there were some issues because this thing is, you know, there's a lot of capacitance has been lost and things like that. And as I say, these little LM3915s and LM3914s, they like to act up a little bit. So this is the reason that, as I mentioned, the actual layout itself, which is this here, will be right below this in an attachment, and you want to build this thing exactly the same way. If you try and experiment with this thing, you'll be building multiple circuit boards yourself. So at any rate, this is pretty much perfected. It works great. You know, this thing works incredible. In fact, you know, this thing is in the mica position here. It, you know, it can be used for basically a component tester. And we'll get into that once this entire unit is built. Now, as I mentioned earlier, this thing was so incredibly time consuming. I've basically worked on this thing nonstop since the last video. And, you know, pretty much as soon as I had this thing completed, I turned on the camera and here I am right now. So that's basically how long this has taken. So I haven't even had time to experiment with the LM3914 surface mount or through-hole version. And that will be done pretty much right after this is done. I'll start working on that other design, and I'll have the LM3914 version ready to go in the next video. So I'll work on the through-hole version and the surface mount version as well. So let's see, what else can I tell you here? I've added some 1 microfarad capacitors in here on the actual IC itself to stop this thing from breaking into oscillation. You can see there's one up here and one down here. This here has been added again to, you know, to deal with the hysteresis between these two LEDs, so basically it doesn't bounce. The 2N5088, you can use that in place of the 2N3904 and get much higher gain. I tested a bunch of 2N5089s and they seem to work okay. They're only rated for 25 volts, but I tested them for breakdown and they didn't break down till 75 volts. So in some cases, if you want to experiment, 2N5089s may work as well for you. The 2N5088 is rated for 30 volts. This is, you know, 27, right? Much, much higher gain than this, and it really, really makes this thing incredibly sensitive. So this here has got the very sensitive transistors in here, and when I design this, and when I actually design the box and get that completed, I might actually use shielded leads because the thing is so incredibly sensitive. I'll get into that here in just a little bit. So let's see, what else can I tell you here? That's pretty much all that's been changed. It's so we have a red LED now instead of the green one, a bunch of added capacitors. Oh, there's a 10K resistor across the very first LED here, across this LED, and that's this resistor, this little blue one right here. Reason being is the LM3915 has been around for many, many years, and you know, it's been around before high brightness, high efficiency LEDs. You basically used, regular kind of diffused red LEDs. And like you saw on the breadboard, you don't really see any kind of lighting. So what happens is when the bar graph goes right to the top LED, and of course the red LED is lit up bright, this will very dimly light. So this LED will very dimly light as this counts down, and then as it passes it and goes to the green, they all go out. So this 10K resistor here is just enough resistance across that LED to just basically keep the thing off. That's all. So that's all that 10K resistor is there for. And again, that was found out in this version right here, because on the breadboard, no problems. On the circuit board, we have, a very dimly lit LED. Now, in order to find that issue out, you can see so there's some flux here, but I don't know if you can see that. I've added a surface mount component there. It's an 0402 part. That's a 10K resistor right in there. So that's what's in between there. And then experimenting with this capacitor here was basically on the back side. You can see that's why the flux is there. There's a bunch of other things that have been changed too. You can see that in this, I've added another resistor over here, right? So I've added this other 20 meg resistor. So again, you can use 22 meg resistors here. You don't need to use the 20 megs. I just have so many of them, I use them in here. And they kind of look nice on the board too, right? So there we go. That's all that's in. These are the tantalum capacitors. You can see there's a tantalum here and a tantalum here. This is a tantalum here and a tantalum here. We'll take a look at the actual layout here in just a moment, the actual component placement map, and that will be included as well in the attachments below. So the backside of this one here, you can see the ground plane layer has been increased a little bit from the other version, not because there was any issue at all, but I'm trying to think ahead here. If, these ICs are going to be coming from an offshore place, I want to make sure that everything is just, pretty much, it's not going to break into oscillation and everything. So just a little bit of added protection. So that's the back side of this board right here. Everything is all soldered in, and this is just my test leads. This is where the 9-volt batteries will attach here. And of course, this will run off to the run out to the test leads here. So this will run up to the test leads to my power supply, and these are the actual sense leads, so that run off to the device under test, is what I'm trying to say. So that's it there. That's the component placement. So what I'll do is I'll get the other piece of paper, and I'll compare this to the paper and show you how the actual component map works. This is the component placement map for the circuit board here, and it's pretty straightforward. So you can see we have 9 volts, 9 volts, and 9 volts. This is where the leads would run off to the 9-volt battery clips. You can see the little holes on the top here where you would mount the little wires from the 9-volt battery clips. A little tantalum capacitor here. You can see the tantalum capacitor here with the polarity mark there. This is the row of LEDs, and as you can see, the little diode symbol. This side here is the cathode for all the LEDs. And as you can see, you just follow it. 10K resistor here, 2.4K resistor here. We have a tantalum capacitor in there, 2.4K. And just as you go along, everything's all mentioned. 100 microfarad, 35 volts, which is right here. And on this side, you can see the VR and the switch and everything. Pretty straightforward. This here is where you will mount your center off switch right here. And just follow the wiring diagram to any standard center off switch, and you should have no problems. These here will run out to the probes. And yeah, this is case ground for a metal project box, and we'll take a look at that here in just a moment. So this will be an attachment just below the video as well, and that will help you populate your circuit board. This is a drill guide so you can mount the circuit board into a project box with ease. Now the project box that I am using is this Hammond 1550 WC. I bought a couple of these things here. It's a nice little enclosure here with a gasket and everything. Now it really didn't need the gasket, it's just what I managed to pick up. It's what they had on the shelf, so you can get one of these things without the gasket. In fact, I think these things go together without the gasket. You could probably just remove the gasket if you wanted to. But it's nice that it's there. I'll still keep using that. So this is the enclosure that I'm going to be using. So basically what you would do with this drill guide here, so I'll just get this out of the way. So this is the top of the box. What you would do is take this drill guide, and what you can do is you can cut this out right along the lines here, so you have a nice little square. You can take that little square and put it onto the box here, and basically get the thing centered, maybe a little towards the top so it's even on each side. So I'll just bend this over the box so you can see. So you can see, something like so, maybe that far from the top, whatever makes you comfortable. It's your project. Once you've got this thing nice and square, on the box and everything is, measured up nice and even, take some tape and tape this on. And then you get your center punch, put your center punch right on the little white dot in every little guide and give it a click on every single dot here. And then what you do is you take a very small drill bit and then you drill out every one of these holes. So the center punch will guide the bit perfectly into the center, and once you have a guide hole, a small guide hole for each one, then you can get the appropriate sized bit. And of course this will depend on the size of the LEDs that you choose and the size of your standoff. So I'm not saying any sizes here, you can choose your own drill bits. And that will give you a perfectly aligned row of LEDs, and if you put standoffs here, it will hold the board perfectly below this. So to give you an example, this is my box here. You can see I've got a nice little clear jewel light on the top. So what happens is when you're putting this thing together, there's a bit of a trick to getting the LEDs aligned as well. So what you do is you put all the LEDs in the board, they're loose and they're not soldered. So basically you put them all in and they're just kind of hanging in there. And then what you do is you take the box, and then once you have your standoffs mounted inside, you kind of hold it like this so the LEDs don't fall out, and you put this up in here. So when you put this in here, just bend these out of the way for a moment. When you put these up in here like so, what you do is you put the circuit board right down into the box like that. And then what you do is you give them just a little bit of a wiggle, and each LED will fall right through the hole, just like that. See how nicely that aligned up? Now when they fall through the hole, what you do is you can put a screw on one of the standoffs or two standoffs, and then what you do is when this is in the box like this, you solder these one side, make sure it's nice, and make sure all the LEDs have been pushed out, so you want to make sure that they're all protruding through the face of the unit here, and solder one row, and then clip off that row with a pair of clippers, the extended leads, and then solder the other row. And then once you've done that, when you take the thing out of the box, everything aligns up. The thing will just slide right into place. The LEDs will just be just like that. This here is right over these two LEDs right here. So you can see these two little LEDs right here. They will shine into this clear jewel light, and that'll look really neat when this thing is working. So you can see, look at that, just falls right into place, just like that. So there's a couple of tricks to help you get your project box working and, make everything work. I'll just remove this here. I bought a bunch of these clear jewel lights, and you can see on the inside here, the two LEDs, they sit directly in the center, and that is because of this right here. So the case of the actual jewel light itself was the threaded area here was 5/8. So if I move this down, that was 5/8. So it's a pretty big hole to drill. But you don't really need to do that. If you want to tap the case and just use the top of the jewel light, you could even thread this thing directly into the case itself. So it just depends on what you want to do. So I figured that would look nice. Now I haven't painted the box or anything. This is all for display, and I have another box here too. This was my experiment. So I'll make another one on this one here, and I'll end up painting these things up and get everything happening. So there's a few hints for you there. I haven't drilled any holes for the test leads. I imagine I'm going to put the switches down here, and the batteries will fit in the bottom. Oh, this is a good thing to show. What I'll do is I will go grab, actually I have them right here, these 9-volt batteries, and I'll show you something. So the 9-volt batteries, I put one in here like so, and another one in here like so, and another one in here. Look at that. How's that for measuring? That's like side to side, perfect fit with the Duracell batteries. Like you can't, you know, it'll pop out actually. So at any rate, so you can sit 3 9-volt batteries nice and flush in the bottom of the box there, and then, you know, you can hold them down with a little, you know, retainer or have something inside the box. But at any rate, that's the reason I chose this box, is it would fit these absolutely perfect. So, as mentioned, I will probably mount my switch here to choose the electrolytic mica or, you know, ceramic, whatever. And I'll probably have an on and off switch here, and maybe the discharge switch here. So that's all to come. And as I design the other LM3914 version and things like that, I'll probably come into another design. I may even extend the actual circuit board itself, and maybe I'll get some solder in switches. I'm not really too sure at this point. As I said, you know, like I've been going since the last video to now, and, you know, as I say, this was finished moments before I turned the camera on. So, I mean, it's been go, go, go. So by the time the next video is up, I'll have even more of this done. I might even have some artwork on the box. I really don't know at this point. It just depends on how quickly things go. So let's take a look at the way this thing works, and I'll give you a few examples. Let's test an electrolytic capacitor. So the switch is in the electrolytic position. I have a 22 microfarad 35-volt capacitor here. So the yellow lead, which is the sense lead, goes to the negative, and the other lead goes to positive. So this is 22 microfarad. No problems with that capacitor. So now you could use that as a reference against, say, another 22 microfarad capacitor. So let's try this one out here. So this is less than the other one, so technically it should move faster. The other one's a brand new capacitor. And I pretty much think we have our answer for this. Now here's the trick. If you leave this attached for a very long period of time, it might slightly try to reform, just like it would do on a Heathkit meter. There's hardly any current here, you know, like it's a 4.7K resistor feeding this thing, and then, you know, on the other side there's 82K to ground, right? But still, that's enough to sometimes make them start working again. Now, if you leave some of the older paper and foil capacitors hooked up for an extremely long period of time, it may count down as well. And of course, that's where common sense is going to come in. You know, like if you're testing a 0.1 microfarad capacitor and it takes half an hour for it to go down, and say it does actually reach the green LED, that doesn't mean it's good. It took a half an hour to get there. The Heathkit IT11 capacitor checker will do the same thing. If you leave capacitors attached to it for a very long period of time, an old 0.1 microfarad, sometimes eventually the eye will open. Again, that doesn't mean it's good. It took an incredibly long time for that eye to open. So down the road, I'm going to create a chart of times. So if you wanted to, say, hook one of these things up, we know that this is obviously leaking like crazy because, you know, it's not even moving off the last, you know, LED there. So I'll create a chart of capacitor times, you know, different types of capacitors, ceramic capacitors. And, you know, of course, some capacitors are lower leakage than others, so they will move quicker. And you can use that as a reference. And you know what? And maybe I'll make just an open post so people can add their own data to it. If they try an odd capacitor of some sort, you can, you know, edit in some data. You know, say I tried the Sangamo capacitor, and you know, it went down at this period of time, and it was a brand new, you know, part or something like that, right? So if people they're working on an older amplifier, or maybe even a switch mode power supply or something that has some odd capacitor, they can look down the list and say, oh, well, this is a good known device, and, you know, it goes down in this period of time. So that would be a very helpful chart, kind of like an ESR chart for capacitors that they have on the old meters. Do I have that meter around? No, I don't. They have a little chart on the front of the ESR meters there. So let's try another capacitor. Let's see which one. Let's try this one here. This one is made by Astron. So There we go. Now again, this is 20 microfarad, and we saw how fast the other 20 moved. Not bad. Not bad. The Astron's doing just fine. That's below 7 microamps. Now I'll let you in on a little secret. The first time I attached this capacitor up, it took about 5 minutes to come down. Then I discharged it. I did it again. It took about 2 minutes to come down. And then I did it a couple more times, and look at how fast that went down. So yes, even though the current is low, it's reforming the old capacitors. So make sure that if you're testing these older capacitors, you get your answers right away, because now technically this cap is reformed. And if it can go below 7 microamps, I betcha I can get a spark out of it. Let's see. Let's see here. Yeah, look at that. Not bad. Of course, I wouldn't trust this thing. So, but anyways, it's still working. Not bad. All right, let's look at some other capacitors. Let's test some 0.1 microfarad capacitors. So we'll test a new one first, and we can use this one here as a reference to how long this should take to go down. So here we go. This is on the paper and poly setting. So that gives you an idea. So let's check out this one here. Another one of these Astron capacitors. Lots of Astron capacitors. They make great examples. There's the Astron here. Again, you can see the Astron there. 0.1 microfarad, same thing. As you can see, this is very leaky. Now again, leaving this thing hooked up for any long period of time, we're going to probably down the road, see a little bit of movement just because it's been sitting there for a long period of time. I'm expecting this one to come down just a little bit, maybe. I'll look for another capacitor here too. At it. Now this one is excessively leaky. This one is not moving. I thought this one here might come down just a little bit. Oh, there it is. It's starting to come down. Now you can see, being attached for an extended period of time, it will go down. Now sometimes they'll stop and they won't move. They'll maybe say get to this lamp here and it'll just stay like that for an incredibly long period of time. And in other cases, maybe over a period of 2 hours, it'll eventually get down here and try to go to the green light. If it takes 2 hours for a 0.1 microfarad capacitor to count down, we know it's bad. You saw how fast this one did. This is the same rating for this little capacitor right here. As you can see, it's moving down one LED. I don't know if we're going to even get lucky enough to go down another LED. So let's try this one right here. Now this is a yellow band Sprague, and I can pretty much tell you that that thing is going to be a dead short, or very low resistance at any rate. All right, this is just going to stay like this. I can guarantee we'll be here for an hour and this isn't going to move. It's one of these yellow writing Sprague capacitors. Any Sprague capacitor with yellow writing on it like that, definite grief. Let's try this one here. This is a brand new capacitor, never been used. So this one is 0.027 at 600 volts. So basically right out of the box. Let's see what this one does, if it does anything. It's always neat to find these old capacitors that have never been used and try and get an idea of, you know, if they've deteriorated. And through so much experimentation and taking these things apart, they still deteriorate. Even with, you know, not being put in service ever, they still don't work. So this is 0.02, so this would definitely be green already. Right, so do I have another 0.02 over here? What's this one? 0.047. So quite a bit higher than this, all right? So we can see that this one here is, you know, not going to move. Probably will after some period of time. Let's try this 0.047. So you can see the difference in these capacitors. We definitely know that these are all faulty. What else? We can try some micas. All right, I'll fish out some micas and I'll be back. All right, let's test out some mica capacitors. Let's test this nice looking little solar capacitor first. So this is on very, very sensitive setting right now, almost to the point of needing shielded leads. No problems, works good. Let's test out this Aerovox one. That's not looking very good. Same value as the solar. So very leaky. Now on this capacitor here, these are usually mica capacitors, but it does not say mica anywhere. So I imagine it probably is. If I had this on the paper and a ceramic setting, you know, paper and poly and ceramic setting, this would definitely move down a lot faster. So this is indicating leakage. I don't know what is in there. It might be some form of a paper. Well, let's just click it to the paper setting. You see, so most likely not. It is most likely a mica, the 1445 series. I haven't looked it up. So click it back there. And you can see, look at it going right back to its leaky self again. Same value as this capacitor here. These are 0.1. Pretty large micas, 2500 working volts this one here is. See if I have any other micas here, more modern ones. Here I do. My bucket of capacitors. So this would be 3900 picofarad or 0.0039 microfarad. So I'll just move this out of the way. And I will attach this here, and here we go. And as you can see, no problems with that mica. Let's try this one here. It says leaky on it. I marked that on there a long time ago. I had this in a transmitter. And I remember it developed leakage under really high voltage. And as you can see, it's showing that. This would only leak at very high voltage. So the tester is working extremely well. Yep, definitely toast. Now you can see what I mean by the leads here. If I move my hands close, it'll settle off if I keep my hands in the same spot. It's just when I move my hands, it's that incredibly sensitive. So you can see it settles off at the fourth light. If I move, it'll settle back off at the fourth light again. And if I move in, it'll settle off at the fourth light again. So just the movement very close. It may need shielded leads. So as long as you don't basically move around or interrupt the test, it should be okay. So I'll see how this goes. I might use a piece of Teflon cable or something. We'll see. All right, I had to just quickly put this in the box to see what it would look like. So here we go. This is on the sensitive setting, so I can just touch the clips. I think that looks great. That'll make a really neat looking project. Very, very sensitive. Quite happy with the results already. I'm not even finished this thing yet. I'm now going to start the LM3914 version. So I'll build a through-hole circuit board and a surface mount circuit board. Once these are done, I'll release the layout to you guys and the schematic as well. So just below this video, there should be 4 attachments. There'll be a schematic, there'll be the drill guide for the project box, there'll be the layout itself for the circuit board, and there'll be a component placement map, and that should get you going on building this version. So enjoy, have fun, and I'll see you soon. Bye for now.